Okay, so I mentioned at the end of the last video that I'm going to derive all of these. I'm actually not going to derive all of them. You already know the antiderivative for some of these. The antiderivative of sine is negative cosine of x plus c. The antiderivative of cosine is sine of x plus c. And we just saw the antiderivative of tangent is negative ln absolute value of cosine of x plus c. The next easiest one to fill in is probably the antiderivative of cotangent of x, because cotangent is just the reciprocal of tangent. So instead of having sine over cosine, you would have cosine of x over sine of x. So it's probably not a big surprise that you would end up doing a u sub for sine of x. And it actually works out where the antiderivative of cosine is ln absolute value of sine of x plus c. Now the antiderivatives for cosecant and secant are a little bit more complex to derive. You can read about it in the ebook if you're interested, but I'm also fine if you just directly use the formulas that I'm going to give you right now. So they are, for secant, it's the natural log of the absolute value of secant of x plus tangent of x plus c. And for cosecant, it's very similar. It's negative ln absolute value of cosecant of x plus cotangent of x plus c. And one of the easiest things that you could do to verify this is you could take the derivative of this function and you're going to arrive at cosecant, or you could take the derivative of this function and you could arrive at secant. And you might have to apply some Pythagorean identities and other trig identities to see that, but that is what is involved here. Okay, so now moving forward, we're actually going to take all of these with us. And so we're going to pretend that we know all of these. And so I know in the previous video I derived the antiderivative of tan. We're not going to worry about deriving that anymore. We're going to pretend that we know all of these, and we actually do. We have them at our disposal, and we'll use those for making things a little bit easier for us in some other questions. And I'll show you exactly what I'm talking about. So let's take a look at example 4 here. So in example 4, we're doing the antiderivative, it looks like my symbol got cut off there, of tangent of 5x. And so let's assume that we know the antiderivative of tangent. Since we do know, it's negative ln absolute value of cosine of x. But we can't do the antiderivative of tan of 5x because that's a composite function itself. So I'm going to let u equal 5x here. My du would be equal to 5 dx. So I need to acknowledge that. I get my 5 dx in the integrand. I get a 1/5 out in front. And this becomes 1/5 integral of tan of u times du. And now we can use the fact that we know what this is. So the antiderivative of tan of u is supposed to be negative ln absolute value of cosine of u and then plus c. So the only thing that we have left to do to finish this example out is just back substitute in for u. So this is negative 1/5 ln absolute value of cosine of 5x and then plus c. So I'm still using that general structure involved with integration by substitution, but now I'm also applying the new antiderivative involving tangent. Okay, let's go to number 5. Let's solve the differential equation. And actually, we're not getting a general solution. We're going to get a specific solution. So eventually, we will know what the c value is in this problem as well. So this work should look like the following. I'm actually going to start it by bringing this dt to the other side. So that way, if we start it as dr equals secant squared t over tan of t plus 1 dt, we can see that we can get our general solution by just integrating both sides. So the integral of 1 dr is simply r. So we get r equals the integral of secant squared t over tan t plus 1 dt. This is a complex looking integrand. This isn't a function that we're familiar with as being the derivative of something else. We can't apply power rule. So this is where I would consider doing a u sub for that entire denominator. And in this case, if you do a u sub for tan of t plus 1, your du is equal to secant squared of t, and secant squared of t dt is exactly what our numerator is. So this actually works out to be r equals the integral of just du over u. So we get r equals natural log of the absolute value of u plus c. Let's plug back in what our u is equal to. So we have r equals natural log of the absolute value of tan of t plus 1 plus c. That is the general solution, but we don't want the general solution to the differential equation. We want the specific solution to the differential equation. So that means we should plug in pi for t and 4 for r. So we get 4 equals ln tan of pi and then plus 1 plus c. And it actually turns out that the tangent of pi is 0. Try to review that unit circle a little bit before you guys start Calc 2, if you're taking Calc 2, because little things like this you want to be comfortable with when you're doing more complicated calculus for sure. So the tan of pi is 0. You're doing the natural log of 1. The natural log of 1 is 0. So c plus c plus 0 is equal to 4, means c itself is going to be equal to 4. So the specific solution ends up being r equals the natural log absolute value tan of t plus 1 plus 4. So there it is. R equals the natural log of the absolute value of tan of t plus 1 plus 4. Okay, number 6. You see a definite integral here. But again, the idea is consider a u substitution for the denominator if some of those other strategies don't pan out. And here, going to u equals x squared plus 5 is going to be helpful, as you can see, because your du would be 2x dx. Slight modification of the integrand takes us to 1/2 integral of du, that's du, over u. But we have to change these limits of integration, and then this becomes an entirely new problem. This is how I've been approaching these definite integrals involving u substitutions. And so when x is -1, I'm going back into this. So when x is equal to -1, we get -1 squared is 1 plus 5, u is equal to 6. When x is equal to 0, you get u is equal to 5. And I know in the past I said maybe switch these when the upper limit is not bigger than the lower limit. But if I switch them, then I have to introduce a negative into the problem. So I'm almost just going to leave it like this. So this is an entirely new problem at this point, and this becomes 1/2 natural log of the absolute value of u, where u is going from 5 to 6. So the final answer, 1/2 times the natural log of the absolute value of 5, that's just the natural log of 5, and then minus the natural log of 6. And if you wanted to, you could apply properties of logs and write this as the natural log of 5/6, but that's not necessary. I mean, this is going to give you the exact same thing as what you would get if you do simplify things with properties of logs. Okay, so hopefully this helps, and hopefully that you see this is a continuation of what we were doing in 5.5, really with this new idea of considering a u sub for the denominator, or as we saw in one of the earlier videos, considering a u sub for terms that involve natural log of x. But that's about it. And in the next video, I'm just going to go through a few more exit problems, so check those out.